Video AI is shifting from passive captioning to real memory, real spatial awareness, and far less token-heavy inference. The big surprise is that current models still struggle with things humans do almost automatically, tracking what happened, where it happened, and when to answer. What connects these papers is a move away from brute force context windows towards systems that compress, internalize, and time their understanding more intelligently. Keep watching, because the details reveal both how far video models have come and the bottlenecks they still haven't solved. Let's explore the first paper, M3-Evol Multimodal Memory Evaluation through Cognitively Grounded Video Tasks. M3-Evol, developed by Ji Huang, Rushun Liu, Sirui Sun, Xinyi Yang, Yin Li, Yixin Zhu, and Yiwu Zhong at Peking University and the University of Wisconsin-Madison, is the first benchmark to isolate multimodal memory in video understanding rather than conflating it with perception or reasoning. Grounded in cognitive psychology, it defines 4 memory dimensions: divided attention for concurrent streams, interference for retroactive versus proactive distraction, interleaved events for temporal organization, and N-back for symbolic grounding and memory capacity. The benchmark spans 2,403 questions over 451 videos, and about 403 hours drawn from Our Video, Video MME, LV Bench, InfiniBench, and CrossVid, with questions generated by Qwen 3, 527B, and manually verified, across proprietary and open models including Google DeepMind's Gemini 3, 1, Pro, Preview, OpenAI's GPT-5, 4, Qwen 3, 5, Qwen 3, VL, Intern VL 3, 5, Video Lucy, and Mathers Agent. The results show substantial gaps from human performance. Models often fall near chance on split-screen source identification, exhibit high intrusion rates under semantically similar interference, fail to reconstruct interleaved temporal order, and lag far behind humans on N-back. A notable finding is that repeating target or interfering videos can improve accuracy, while temporal source grounding is consistently weaker than spatial grounding, revealing a core limitation in current transformer-based memory mechanisms. Let's explore the second paper, Stream 3D VLM Online 3D Spatial Understanding with Incremental Geometry Priors. Stream 3D VLM, developed by researchers from Zhejiang University and Tencent Hunyuan, is the first online 3D vision language model built for streaming video rather than offline clips or full scene scans. Its core novelty is to treat when to answer as part of autoregressive next token prediction, using special is less than, SEP is greater than, and is less than, END is greater than tokens, so the model learns to stay silent until sufficient 3D evidence arrives. To recover geometry without explicit 3D sensor inputs, it incrementally injects temporally aligned priors from the feed-forward reconstruction model, Stream VGGT, through a lightweight visual spatial feature integration module, then compresses long histories with geometry-adaptive voxel compression, which clusters 3D voxels by spatial proximity and aggregates them with dual attention. The authors also released Stream 3D 1M, a 1,003,203 question dataset, spanning 5,154 scans, and Stream 3D Bench, a 10,037 sample benchmark over 29 tasks with a new answer timing accuracy metric that scores both correctness and temporal precision, based on Qwen 2.5, VL 3B, 7B, Stream 3D, VLM 8B, reaches 65.9% average accuracy on VSI Bench, outperforming Gemini 2, 5 Pro, and other 7.2B scale baselines, and it achieves 75.4% answer timing accuracy, with only 62 milliseconds TTFT and 0.39s end-to-end latency on Stream 3D Bench. It also improves offline 3D tasks such as Scan QA, Scan Refer, and Scan 2 Cap, showing that online interaction and strong 3D spatial reasoning can coexist in one model. Let's explore the third paper, Video 2 LoRa Parametric Video Internalization for Vision Language Models. Video 2 LoRa is a new parametric video internalization method for vision language models built on SMOL VLM, 2500M, and 22B from the authors at the University of Maryland, College Park. Instead of keeping video frames as visual tokens in the context window, A frozen small VLM 2 encoder produces layer-wise hidden states, and a perceiver hypernetwork converts them in one forward pass into a video-specific LoRa adapter. The frozen model then answers any later text query with 0 visual tokens. Trained only on 12 frames at 384px using cached teacher-generated captions and summaries from fine video spans, the method is statistically non-inferior and equivalent to direct in-context video inference on all 5 captioning benchmarks: ActivityNet Captions, PLM RDCap, PLM RCap, VDC, and Carabench, and on 7 of 8 video QA benchmark scale pairings, including zero-shot transfer to NextTQA, ActivityNet QA, PLM SGQA, and VidCap Bench. It preserves performance up to 1024 frames and 1024px, where direct inference often degenerates, while cutting answer time visual token load by up to 1,500 times and time to first token by 6 to 80 times. On VidCap Bench, TTFT drops from 6.45s to 0.55s at 500M, and from 7.06s to 0.58s at 2b. The paper also shows that independently internalized adapters for video chunks can compose in rank space, suggesting a path to scalable long video internalization. That's a wrap on today's AI paper highlights. Thanks for watching.